So good morning everyone. Welcome to the final session or final day. And my morning will be by noon will be. Uh, so we have a session on RAMJET and SCRAMJET, and then followed by so we'll go to lab, have a small session on the PIP. Then after that we'll come back and then have a small closing. Professor Mehta, retired professor from IIT Madras, is going to join us. Yeah, so please tell others also to join. Also, you ask them. So after the lecture, we'll have a small session on like you have to give a feedback on the course, and then there we'll have a small test. It is like 10 minutes, fill in the blanks, because as per the GAN guidelines, we need to conduct.
Okay, good morning everybody. So this is going to be my last lecture to your class. Okay, so just to recap quickly what we have done. From Monday onwards, we looked into the gas turbine propulsion systems. We looked at turbojet, turbofan, turboprop, turboshaft. It's all gas turbine based propulsion systems. Then we also moved into the RAMJET and SCRAMJET very briefly to differentiate that they don't have any rotary components like that of the gas turbine engines. And the combustion can take place under subsonic conditions or supersonic conditions. Accordingly, we need to have a theory. We looked at the theory, that's the Rayleigh flow theory. I used that. We also tried to work out the problems. And then we went on to discuss about shocks, because when we talk about such high supersonic speed, shocks will be prevailing. So we looked at normal shock when we learned how to use the NACA table, which is designed for normal shock. And we also went through the oblique shock theory, and then we were able to see that if we can resolve the flow normal to the shock, oblique shock, then we could use the normal shock tables. And also we looked at the shock interactions and reflections, and then from there we went on to supersonic inlets, looked at convergent divergent inlets starting problem, and then normal shock inlets, external compression inlets, mixed compression inlets. And then we tried to work out few problems on external compression, mixed compression inlets. Then we looked into the nozzle flow structures, the possible scenarios. It could be under-expanded or over-expanded situations. And then we also had this experimental section on Schlieren, lectures from Dr. Madan on Schlieren and mixing systems, sprays, and then lab demonstrations. Today it will be our final lecture that will be on RAMJET and SCRAMJET, and if time permits, we'll look at turbo RAMJET. Yeah. And so here is the RAMJET propulsion system. So where you see that you have an inlet which is dominated by shocks. First of all, let's look at the geometry of the inlet. The geometry is of convergent and divergent. It must be convergent divergent for a RAMJET operation. The most important thing what you see here is that it can have, mostly it will be of mixed compression inlets because of the Mach number at which it travels. And then you see, this is what is very important. This is what is called as a terminal shock. After that, the flow becomes subsonic. That is very important for RAMJET propulsion. And we discussed that to have the best pressure recovery, we place the shock slightly downstream of the throat of a convergent divergent inlet. Then you have this combustion taking place. Combustion taking place under subsonic conditions. At the end of the combustion, the flow is accelerating in the convergent divergent nozzle, becomes m equal to 1 at the throat, and then becomes supersonic. And here you can see that there is no rotary machines. Everything is based on the ramming effect because of the speed. Normally, the RAMJETs are very effective in its operation between Mach number 3 to 6. The question is, can we operate a RAMJET greater than Mach 6? There are some challenges. That's what we're going to look at. If you go beyond Mach 6, then we need to decelerate the flow. We have to bring it to subsonic. The process of deceleration involves increase in static pressure, increase in static temperature, static density. Now, all of them will be culminated in the combustor with very high pressure, high temperature. At that speed, you have mechanical stresses. On top of it, you will have this thermal stresses. So, which is not a very favorable environment at that high speed operation. So, when we try to go above Mach 6, this effect of pressure, temperature, density is so pronounced, it's no longer advantageous to decelerate it to subsonic speeds. Now, as I did mention, the structural design will be a problem. The pressures are very high and the temperatures are very high, and you have to allow the flow to encounter the terminal shock. So, which means that if the Mach number prior to the normal shock, terminal shock, is above 1.6, then you will have a penalty again on the pressure recovery. And heat transfer rates will be adverse. And because of this temperature, the fuel will also dissociate, and effectively we will not be able to harvest all the useful energy for this one. So operating RAMJET above Mach 6 is not a feasible solution because of the thermal loading and the mechanical loading happening in the combustor. Okay, now what is the solution if you want to go beyond Mach 6? The solution is not to decelerate the flow to subsonic. So it is partially compress and decelerate the oncoming air. The main thing is to avoid the terminal shock. The only thing that makes it a subsonic combustion is the terminal shock. So eliminate the terminal shock. If you eliminate the terminal shock, then we can have a supersonic flow coming into it. So that is the solution if you want to go for flight speeds above Mach 6. So this brings us to SCRAMJET engine. So which means that the flow entering the combustor will be supersonic. So the geometry wise, you can see the inlet M greater than 1. We are nowhere trying to bring it to subsonic, so the inlet geometry is convergent. Again, it's dominated by shock waves, and then you have the injection of fuel. The charge enters into the combustor. At supersonic conditions, the fuel is injected and it is mixed, and then it is burnt with possible shock waves present in it. And then at the end of the combustor, still it is supersonic, then the flow continues to accelerate to supersonic speeds. Now let's identify what are the main differences in RAMJET and SCRAMJET engine. Now when you look at the main difference, the differences are there in every component of this engine. So if you look at the inlet diffuser, number one, if you look at the geometry, there is difference in the geometry. For RAMJET, it is a convergent and divergent geometry, and for the SCRAMJET, it is just the So then if you look at the shock train, then you see this only a difference in the shock train. You have a terminal shock or a normal shock in RAMJET to make it to M less than 1. Here there is no terminal shock in case of SCRAMJET engine. So there is a difference in the geometry and the difference in the shock train. And when you look at the combustion process, combustion takes place under subsonic conditions, whereas the combustion takes place in the supersonic conditions. And then again, because the combustion takes place at subsonic conditions for ramjet, you need to accelerate from subsonic to supersonic. So you need to have a convergent divergent one. The combustion in terms of scramjet, the charge is already at supersonic speed, so you don't need anything of convergent, which is going to be detrimental. So you need to have only a divergent section here. So that's the difference between the two systems here. Okay, so now the reference stations of RAMJET and SCRAMJET is given here. So now if you can look at this, you can see that the cycle diagram, is much more simpler. Here is the unperturbed free stream conditions here. When you look at this, the compression is taking place 0 to 3, and here it is 1. This is the actual engine. This is the actual engine. What you see is now, then you can see that this is external, this is external. I will come back to this because you don't have anything like, we can't say, they can't say this is a ramjet engine, because this has to be integrated as part of a vehicle. That's very important. So the entire undersurface of the vehicle will be the inlet. The entire after body of the vehicle will be the nozzle. Otherwise, you will have, okay, let me finish this one. Okay, so here it is 0, so here it is 1, compression, then it is combustion taking place, 4, and then this is, and then this is the 10. So here it is external compression, internal compression, combustion, internal expansion, external expansion. This is for ramjet. The cycle diagram remains the same. So here it is 0, 0, 2, 1, 1, and this is 3, and then from here it is going to 4, combustion, and then internal expansion, and then external expansion. So this part is external, this is internal, this is the combustion, this is the internal, and this is the external one. So this external compression and external expansion takes place due to the aerodynamic streamlining of the undersurface of the vehicle. So which means that brings to this point that, as I said, this is not, I can't call this as a just, oh, this is like a turbojet engine. We can say this is a turbojet engine, but I can't say this is a turbojet engine, because this has to be integrated as part of the vehicle. Turbojet and turbofan engines can be easily transferred between different aircrafts, but it's not possible with ramjet or scramjet. The main reason is that you can't really hold it with pylons, and then at that speed the bound layers will not be favorable. It will really bring down the aircraft. So the that's what it says. Making hypersonic axis symmetric and attaching it to engines with pylons can produce external drag, which can cancel the internal thrust and create the internal passage narrow, such that the flow is dominated by wall effects. And also, these hypersonic vehicles have to fly at very high altitudes where the densities are low, and the engine should not suffocate due to lack of required airflow. So it has to be fed with the airflow so that it can mix with fuel. And so this clearly tells us the good aerodynamic integration is essential. So now here you see this. This is the engine. This is the engine. Now you can see that the entire forebody of this vehicle will act as an inlet. So I can say that this is vehicle, then probably this is where the inlet is, and then this is the after body of the vehicle. So here is this vehicle here. So this will be the engine. So this entire undersurface will be an external compression. The entire after body will be the external expansion. Because it flies at such a high speed, we really need this. Otherwise, we can't really direct air, that required amount of air, into the engine. Otherwise, you will have an engine of very high, like this. This is how it will be. So otherwise, if we don't have an integration of the engine with the underbody aerodynamically streamlined, then it will not be possible to operate it, because you can't have an engine with such a big inlet and such a big nozzle here. Okay, so you can't operate it like this. So that's why the integration is very crucial. And normally, when you look at scramjet engines, the combustion taking place at supersonic speeds. So you have high energy fuel, mostly cryogenic fuels like liquid hydrogen is the most promising candidate for combustion purposes. So here again you see this is again a schematic. So you have an external compression, internal compression, and then combustion is taking place here, and then internal expansion and external expansion. Now, why is it important? I think I explained some of the things before. So one way to capture the required airflow is to use the entire under forebody of the vehicle as a compression surface. So because we are going to use the undersurface, it has to be perfectly aerodynamically streamlined with no defects to cause any flow suppression, any distortion. Otherwise, we will lose all the mass coming into the engine. Should be carefully shaped for high aerodynamic streamlining of the flow. At supersonic, hypersonic speeds, air has no warning that the vehicle is approaching until it encounters the first oblique shock. So when you look at a vehicle here, so if we can say that this is so the shock starts forming even at a very early spike or the forebody of the vehicle, where the engine is somewhere here. Then you have this one here, the expansion taking place here. So then you have this series of compression ramps, external compression ramps, maybe here, and then the combustion taking place here. So if these things are not happening, then nothing will be entering into the engine. So everything will be, we will not get any thrust produced at all. No mass will be ingested. The stream tube of air is enormously large. This is what I mentioned. The stream tube of air is enormously large. So which means that having just say that this will be much larger. This is practically impossible. So the stream tubes are much large. The physical opening of the engine larger than the physical opening of the inlet. So hence it is important to effectively direct air into the engine. So definitely it has to be integrated to the undersurface of the vehicle, where the entire underfloor body will become an external compression inlet. Once the air is injected in the engine, it will be compressed and burned in the combustor. It will require nozzle exit area much larger than the original free stream captured area in order to produce good thrust. Otherwise you can't produce. So the entire after body will become a nozzle of it. Not feasible to fly with such a large nozzle as a conventional nozzle of this size. It will be too heavy to carry along. So which means that the entire after body underneath the vehicle is used for free expansion surface. The entire underside of the vehicle must be carefully designed to accommodate correct engine performance under all flight conditions here. So it comes with challenges here. It is extremely challenging. That's why very dedicated space centers like NASA and SpaceX, they carry out these kind of programs, because imagine you have to work over a wide range of Mach numbers, Mach 0 to just given a number here, but Mach 10 is still very high range of speeds, wide range of speeds. So which means that you need to have a full facility to accommodate that flight speed range. And then other challenges, having a stable combustion, efficient mixing and combustion in supersonic flow with a very finite volume is again a big challenge. That's why one of the things to overcome this is to go for high energy content fuel, preferably hydrogen is used there, because it has a higher calorific value. It's also having a higher flammability limit between 4 and 75, and that's why it is hydrogen is used as a fuel. And whenever you go at speed, speed means you are increasing temperature, higher the speed. So thermal stresses will be a problem. When you have thermal stresses, it can affect the strength of the material, the structural integrity. It's a very challenging in the hostile environment. And if you have to develop analytical tools, it's very highly compressible flow. So you have to have a very dedicated predicting tools for this one. Ground testing and flight testing, imagine how complex it is going to be. So that's why very dedicated places carry out these choreographic measurements. Here is X-43. The first pre-flight SCRAMJET was tested in 2001, June. The first attempt failed. And 2004, March, the second attempt was successful, Mach 6.8. In November 2004, the third attempt successful, Mach 9.68. It flew for maybe 10 to 12 seconds. That's the demonstration of concept. Then afterwards, it landed in the sea. Yeah, that's all. So it's still in the development phase. So now you can see the comparisons here with the X-43, the SCRAMJET engine above. Now you know the full working of the SCRAMJET here. It has an inlet, it compresses the air through a series of oblique shock waves and feeds the air into the engine, and combustion takes place under supersonic conditions, and then the expansion takes place in the after body of the vehicle. And if we can't have it as a standalone engine, the other drawback here, what you see here, is it needs to be carried in a carrier aircraft. I think this is a B-52 aircraft. It has to be carried up to certain altitude, and then you need to have a booster to fire it, take it to the right Mach number to ensure that ramming effect is there. Then RAMJET or SCRAMJET can operate. Now these are the challenges, because you can't start from Mach 0. On the other hand, if you look at the conventional jet engine, you can go all the way from Mach 0 to, we're talking about, let's say if we're going for military applications, go up to 2.5. with the afterburner. So this is the main advantage with this normal gas turbine based engines. But the drawback with a ramjet, you just only a speed, but you can't take it off from the ground by itself. Now, one of the ways to handle this is to go for a turbo ramjet propulsion, which could be operated from ground Mach 0 to go all the way to Mach 5. So turbo ramjet comes in two configurations, one under wraparound turbo ramjet or over underlay turbo ramjet. SR71 Blackbird will be using this wraparound configuration, and the next generation of Blackbird, Lockheed Martin, they use over under layout turbo ramjet. And European Hypersonic Transport Vehicle Program also, they were doing this on the over under layout. Now let's look at what is wraparound turbo ramjet. So here you have a flexible flap, control mechanisms are there. When it is at rest, the vehicle is with the flap, the flow enters into the inlet. So here you see it's a subsonic inlet here of diffusing geometry. The flow enters in and passes through the inlet, pressurized in the inlet, then it is pressurized in the compressor, then you have the combustion taking place. The burn gases expands in the turbine produces the work, and that work is used to drive the compressor. Rest of the gases expand. Here in this case it's an afterburner, and then expansion takes place in the nozzle. Now when you have reached the required ramming Mach number, maybe 2.5 or something, that range, then the flaps can close the entry. Before it closes, it can go to the dual mode of operation. So where the air also partially gets into the engine and also gets into the ramjet. Then it closes and full 100% operation with the ramjet, where the air enters in through the inlet, and then you can see this inlet, such a long inlet. You need the longer inlet, and then combustion taking place, where the afterburner of the turbojet becomes the main combustor of the wraparound configuration, and then it burns and then it expands in the nozzle. This is the wraparound turbo ramjet configuration. So what all I have explained here, you see the same stuff here in this schematic. So SR71, just give you a bit more information on the speed ranges here. So there are different 4 regimes of operation. So region 1 from Mach number 0 to 0.5. The ramjet is totally off because of the flap position here. It's only turbojet is on and afterburner is off. We need afterburner only for a moment to boost and to augment the thrust. Then for transonic regime from Mach 0.5 to 1.5, still the ramjet is off, turbojet is on, and then for transonic you use the afterburner. Then when you go beyond Mach 1.5 to 2, start the ramjet. Go in parallel with a turbojet, and then the afterburner is off. Then fully a turbojet is off from beyond Mach 2.5 and 6. Only ramjet is on, and you have this ramjet operation. Now this sort of a scheme is the same whether it's a wraparound or over under layout configuration. This is approximately the range of the scheme that's being followed for the speed range. Now let me draw the cycle diagram for this wraparound turbo ramjet. So let's have this enthalpy on the y-axis, and here is the entropy. Now let me start with a low Mach number operation and perturb free stream condition here. Let's the pressure P0, and then it goes all the way to the inlet 2, and followed by that number 3, 2 to 3 is the compressor. Here is the compressor. And then 3 to 4 is the combustor, and 4 to 5 is expansion. 4 to 5 is expansion in the nozzle. Four to 5 is expansion in the nozzle. And then 4 to 5 is expansion, and then 5 to 6 is the afterburner. 5 to 6 is the afterburner. And then 6 to 7 is the expansion in the nozzle. 5 to 6, then 6 to 7. Now, on top of it, when it has reached the appropriate Mach number, then this is what you see here. The high Mach number, you have this inlet going from 0 to 8, whichever the place is, depending on the speed. Then the combustion takes place. 8 to 9, the combustion takes place. The important thing here is that they participate in the same combustor. So if it is at a different combustor, over under layout is a different combustor. So which means the thermal barrier coating material could be used, could be different. But here it is the same. So likely the peak thermal limit here, the thermal limit tau lambda, could be the same. And then it expands here. This is the cycle diagram for the wraparound turbo ramjet. So here you see the SR-71 Blackbird. It is the fastest manned aircraft with Mach 3 something in that range. So you see the shock diamonds and in the flight. Yeah, so it's the only manned fastest aircraft operating using a turbo ramjet up to Mach 3.2. So here is the over-under layout configuration. This operation regime is the same as before, but here the principle is that the turbojet, this is the turbojet engine. Now you can see the turbojet engine goes deep into the fuselage of the vehicle, goes into the fuselage, and ramjet is still on the undersurface of the vehicle. The over-underlay configuration will make the engine much more bulkier compared to the wraparound ones. So now here the flow will get into this engine inlet, compressor, combustor, turbine, and then afterburner then you have the expansion in the nozzle. Once you have got it at the right one, then the flaps will be open. So this becomes the inlet once it has got to the right Mach number. So the flow will come directly into through the undersurface inlet, external compression, internal compression, and then combustion takes place. And then you have this nozzle here. The beauty of this over-under layout is that it has only one inlet and one nozzle. We'll see that a little bit later on. So if I wanted to draw the cycle diagram for this, which is very similar to the wraparound configuration, here if it calls an unperturbed free stream condition, so from here it goes to the inlet in the turbojet engine to 2, and 2 to 3 is the compressor, 3 to 4 is the combustor, 4 to 5 is the expansion in the turbine. Thereafter you have afterburner. So afterburner is 6, and then expansion in a 7. So now you can see this is where we started in the very first lecture, a simple turbojet with an afterburner. And now so once it has reached this appropriate speed, then the flaps are retracted. Compression goes from 0 to 8, depending on the speed. We don't know the position. The pressure is built up depending on the ramming effect, and then that will be 8, and from 8 to 9 the combustion will be taking place. Now here you can see that this is totally a different combustor. So it can be either at the same level here, or it could be at a different level. That's one thing. But mostly it may be of the same level of the different for the practical reasons. And then it expands 9, and then expands points here 10. Okay. So here is the SR72, which is operated on a over-under layout configuration. So it's a turbine-based combined cycle with merges a modified production engine turbine with a dual mode RAMJET SCRAMJET to accelerate the vehicle from a starting Mach 0 to Mach 6. The turbine provides thrust up to and beyond Mach 3, and then the RAMJET takes over. The common inlet, that's what you see here, the common inlet provides the air to both turbine and RAMJET, and the exhaust from both are exited through common nozzle. That's the uniqueness of it. So here is the common. So here what you see above, this is the SR72, and then you see the details of what is happening here. So this is a common inlet and common nozzle, and then it has a variable inlet and nozzle ramp opening to close to match the cycle requirements. So this is expected to be tested soon, maybe 26 or 20, next 2 years, I think this will be tested. So when we looked at this advanced air breathing propulsion engines, we looked at different inlets, looked at the combustors, subsonic, supersonic combustions. When you look at the exhaust nozzles, nozzle flow structures, shock diamonds, under overexpanded, under-expanded, rally theory you looked at, wraparound configuration, over-under layout configuration, the most advanced mixed compression inlets, the cycle diagram of this engines. Looked at gas turbine cycles, inlet, nozzle, combustion, ramjet, scramjet, double ramjet in this week. Yeah, there's only one thing I need to say. Good luck. Okay.